Assalamu alaikum students. Article for today is motion of charged particle in a uniform magnetic field. If I want to discuss the motion of charged particle in a uniform magnetic field, first I need to understand the thing what is meant by this term, that is uniform magnetic field. To understand this thing, what is meant by uniform magnetic field, we should keep in mind two things, right? Number one, if the field lines, all of the field lines, they are directed in the same direction, right? Firstly. Number two, distance between the magnetic field lines does not change. It remains same over the long passage. So that means the field is uniform. Firstly parallel and then equidistant. So that shows the uniform magnetic field. And the uniform magnetic field is represented by, as I've discussed in my previous lectures, that it is represented with the help of a dot or cross. If it is directed out of the screen or out of the page, that means we are going to draw a dot for that. And if I want to represent a field, a magnetic field which is into the page or into the screen or away from you, it should be drawn or indicated with a cross, right? So here I'm going to draw a magnetic field, and I'm going to release a charged particle in that magnetic field. Okay, so as you can see that we are having a uniform magnetic field which is directed into the page, and there is a charged particle having q magnitude, and it is released in this particular magnetic field. Two things one thing you should be aware of is that whenever you want to release a charged particle in uniform magnetic field, make sure that charged particle is released in perpendicular to the direction of magnetic field, right? So what does that mean? That means consider if the charged particle is in this direction, if the magnetic field lines is in this direction, that is of negative z-axis, and then in that condition v should be perpendicular to it. So if I'm releasing according to this diagram, so the direction of v is like this. So there is a b is basically into the page, right? It is not having any angle, it is having an angle of 90 degree, right? So according to this thing, if I'm going to release this charged particle in the magnetic field which is perpendicular to the velocity of the charged particle, right? So now if I'm going to release this charged particle, what is going to happen? This charged particle will not move in the linear path, rather it would change its linear path into a curved one. Now the question arises, why it happens? Why the linear path of the charged particle has been changed, right? Like it should go in the forward direction, right? According to the thing which we know, but it changes its path like this. It is having now a curved path. So why does this happen? Why the charged particles in the magnetic field, they follow a curved path? This happens because of the magnetic force which acts on the charged particles. This magnetic force is basically responsible for producing the curved effect, and we know that the magnetic field is basically providing the centripetal force. Now what is centripetal force? Centripetal force is the force which compels the body or any charged particle to move in the circular path. So here this centripetal force is provided by the magnetic force, right? Now the question arises, why this is happening, and how can we have told that it occurs because of the magnetic force. So what is the direction of magnetic force, right? So to get that direction, I'm going to use Fleming's left hand rule, and according to that rule, what is going to happen if I'm taking my the forefinger in a negative z direction, right? It is the direction of B, and my middle finger is in the direction of positive x-axis. This is the direction of velocity. And now talking about the direction of a magnetic force, which is definitely acting upward, in the upward direction, that is along the y-axis. So this is the thumb which is indicating the direction of force. So at this point this is going to be happen. So because of this force which is basically acting in the force which is acting in this particular direction, like at this point, or you can say at this point, the force is actually acting in this direction. So because of that force, this force, the charged particle will definitely leave that linear path and move into the curved path. So this is the basic force which is responsible to move that particular charged particle in the circular path. So now I'm going to show you that if this is the direction of the force, what is going to happen if we are taking that charged particle to the next step, right? So for the next step, what is going to happen at this particular point? What is going to happen? This particular charge particle, it is going to it should move like this. It should have a movement in this direction. But what is going to happen? The charge particle is going to move in this direction. And why does it happen? It happened because of the magnetic force. The magnetic force at this point, if I'm going to take, this is the direction of velocity, right? Magnetic field into the screen, and the direction of velocity. The direction of velocity has been taken to be, okay, so this at this particular point, the direction of force would be like this. This is the direction of force, right? Now what is going to happen at the next step? This charged particle should move in this direction, right? But it is not going to happen. This charged particle is going to move in this direction, having velocity v. Why does it happen? It happens because of the direction of the magnetic force. If I'm going to check the direction of magnetic force at this particular point, now what is going to happen, that the direction of velocity is like so according to Fleming's left hand rule, the direction of force be like this. What would happen at the next step? At the very next step, this charged particle should move along this direction, but it is not going to happen. Why? Because it is going to move in this particular direction. And why it is going to happen? Because of the magnetic force. And the direction of magnetic force, if I'm going to take that, the direction of magnetic force would be downward, right? Then at the very next step, what is going to happen, that the direction, this charged particle should move in this particular direction, but it is not going to move in this direction. It will change its path in this direction. And why it happens? Because at this particular point, if you are using the Fleming's left hand rule, then the direction of force would be like this. So at every step, at every point which you are going to take, the direction of velocity would again such like that it is going to have a circular motion, right? And the direction of force would always be, at any point if you want to see the direction of force, it would be inward. So because of this inward force, it is known as the radial force. One name of it is the radial force, and other name you always know that it is the centripetal force, or simply the magnetic force, right? Why it is known as radial force? Because it is acting along the radius, and centripetal force because it is compelling the charged particle to move in the circular path, and it is acting because of the magnetic force. And we can see that at every point, if I want to calculate the if I want to see the direction of velocity, the direction of velocity at every point is basically along the curved path at every point. Now if I want to see the direction of velocity, this is the direction of, because of the magnetic changes, right? Otherwise it should be the tangential velocity. So now this particular circular form, if I'm going to draw a more neat diagram for this, it will be like, so this is a neat diagram, as you can see. So this charged particle is making a circular path, right? The movement is in the anti-clockwise direction, as you can see. Now this circular path, we are going to have a radius. Definitely for this circular path, we are going to have a radius which is shown by the symbol r. Now moving towards the derivation stuff and the calculation part, what is going to happen? We know that magnetic force is responsible to move that charged particle in the circular motion, circular path. So that means centripetal force is provided by the magnetic force. So I can write Fc is equal to mv square divided by r, right? Now the formula for the magnetic force, this is going to be q v cross b, right? Now if I really want to equate these two forces, what I'm gonna do, I'm going to open this cross product. Okay, so now you are seeing that I've equated both the forces, that is magnetic force is equal to the centripetal force, putting the value of magnetic force, which is qvb sine of 90 degree. Why I'm putting 90 degree over here? Because initially we have mentioned that velocity is perpendicular to b. Now in this condition, now you must know or you must have an idea now that why we were accelerating or releasing that charged particle perpendicular to b, because in that condition magnetic force would be having a maximum value. So I can write q v b, that is the maximum force. This is equal to mv square, which is basically the value of centripetal force, right? So from this, if I cancel out v on both sides, it is basically having a square. So the equation would now become q b equals to m v divided by r, right? And from here, if I want to get the value of v, so what is going to happen? The value of v would be equal to q b r divided by, this is r, q v b r divided by m. So this is the value of velocity which we really need if I want to know the direction of the magnitude of velocity, that what would be the value of velocity for the charged particle moving in that particular magnetic field. Since we know that the this is going to be a magnetic field, uniform magnetic field, so as you can see that this velocity is depending upon q by m. Q, that is the charge which will remain constant, m mass of that charged particle, which is also going to remain constant. We are left with b, since this is the uniform magnetic field, so the value and magnitude of direction and magnitude of magnetic field is not going to be changed, so this is also constant. Resting is r, that is the radius. So if b is not changing, that means r is not going to change. So for all this, if we know all these things, we can calculate the value of velocity in this particular case. Now you must be wondering, how can we calculate the radius? When we basically performing this experiment, we do have a particular scale, and from that we can calculate the radius very easily. Okay, So from the previous step, we had derived the value of v, which was q which was q b r divided by m, right? Now from this equation, if I want to get the value of r, so what is going to happen? I can calculate the value of r from this relation, and this by arranging this particular equation, what I'm going to get, I will receive m v divided by q b. So we can easily calculate the radius if we know the value of velocity of that charged particle very easily. But usually this radius has been calculated experimentally, right? Now moving towards the fact that if we are not provided the velocity, then initially how can we calculate the value of radius? So for that purpose, what we are going to do, we will equate the kinetic energy of work done equals to kinetic energy. You have read the relationship in first year, that was work done is equal to kinetic energy. So using this particular relation, what I'm going to get, half m v square is equal to EV, that is the potential, right? This is the potential provided by the battery, because potential is basically responsible to move the charges from one point to another point. So basically in this case, when they move from one point to another point, work is going to be done. So this from this relationship we can calculate the value of velocity, and the value of velocity would be calculated as v square. So in this case, v square can be calculated as 2e. E is the charge on that particle. This v is going to be the potential offered by the battery, and 2ev divided by m, right? And if we want the value of v, I will definitely put an arrow under root, that is 2e v divided by the m. Make sure this is the velocity and this is the potential which is offered by the battery, right? So if we know this particular potential which is offered, obviously we know how much potential we are going to provide. So if we know all of these values, we can easily calculate the value of velocity. Okay, now moving towards the next formula, next information which we can get from these two equations. We know the relationship V equals to R omega, right? And if we know this particular relationship, we can easily calculate the angular velocity. The value of angular velocity would be omega equals to V by R. Now if the value of v, which initially was, we know that value, that was q b r divided by m, and this r is going to be as well here, so this r and this r would be cancelled out, and omega, that is the value of omega, comes out to be q b divided by m, right? So this is the value of angular velocity, angular velocity or angular frequency, which we are going to which we can easily calculate through this relationship. Now omega, which is the angular frequency, now after that we are going to find the time period of that is the time required by the charged particle to complete its one revolution. How can we calculate that? We know that the value of omega the value of the formula omega equals to q b divided by m, right? If I put the value of omega, which is basically 2 pi by t equals to q b divided by m. From here we can easily calculate the value of t, and this is going to be like t is equal to 2 pi m divided by q b. So this is the next thing which we have determined, that is t equals to 2 pi m, that is the time period. Frequency, now we know that time period is basically the inverse of reciprocal of frequency or inverse of frequency. So if I want to calculate the value of frequency, it would be the inverse of this value. So I can write q b divided by 2 pi m. Now the very next thing which we want to calculate for the kind of like if I want to know the kinetic energy of the charged particles when they are moving in a circular path, how can I calculate that? We know the formula for kinetic energy, which is basically kinetic energy is equal to half m v square, right? So if I put the value of v from here, what is going to happen? Half m q square b square and r square divided by m square, right? So from here we can see this m would be cancelled out, and the value of kinetic energy comes out to be half q square b square r square divided by m. So that's how we can easily calculate the value of kinetic energy for the charged particles moving in a circular path. Okay students, up till now we have derived all of these formulas, and in all of these formulas you can see that radius is very much important. To determine the velocity we need that radius, but in case of angular frequency, time period, the frequency and the not kinetic energy, these are angular frequency, time period and frequency, all of these are independent of r. So for all the circular paths, if the charged particle is moving in a circular path which is greater than r, like suppose if this is the condition, this is the radius is r, and if a charged particle is also moving in this condition having a radius r prime, and there is another radius as well having a radius of r. So for all these radiuses, the value of angular frequency, time period and frequency would remain the same, right? Why it happens? It will happen because in the formulas we can see there is no involvement of the radius, but when it comes to velocity, velocity is depending upon this radius. So radius is very much important in this case, so velocity will change if the radius changes. Okay, so this was the case when the charged particle has been released in any uniform magnetic field perpendicularly. If you can see it will experience some maximum magnetic force and it will move in the circular path. And we know very well, if I'm going to release this particular charge particle along with the direction of magnetic field, we are going to receive theta between them equals to 0 degree, and ultimately sine 0 degree would be equal to 0. So no force will be experienced by this charge particle, and the charge particle will not move. What will happen if I'm going to release, like suppose this is the magnetic field, and if I'm going to release a charge particle not perpendicular, not parallel, along some angle theta, then what is going to happen? So for this case, we are going to have the next lecture in which we are going to study that what will happen if I'm going to release the charge particle with an angle theta. So thank you so much.